This is the problem on the temperatures on the moon, and it reads as follows. On the moon, the surface temperature ranges from 375 kelvins during the day to 1.00 times 10 to the second kelvins, or exactly 100 kelvins. What are these temperatures on the Celsius and Fahrenheit scales? We have given two temperatures and we're supposed to convert them to Celsius and to Fahrenheit, which means we're going to come up with four answers. So we have, I can leave it at that one. So TK is given. The first TK is given as 375 kelvins, and the second TK is given as 100 kelvins. Okay. And I don't think I need this box here. It's pretty much just converting from one temperature to another. So in order to come up with the Celsius temperatures, I need to subtract 273, and then I come up with the Celsius temperature, so TC. I know it says 273.15, but it looks like we're truncating after the integers. So obviously I can write down the result here, 102 degrees Celsius, and on the other one I would do the same thing, minus 273. So in Celsius that's going to be minus 173 degrees Celsius. That was supposed to be a C. I think I might need a little bit more space. Okay. Then the Fahrenheit temperature. And here what I need is the conversion. Temperature in Fahrenheit equals the Celsius temperature times 1.8, and you're probably finding in places that it says 9/5. I just like to write down the 1.8 instead of the fraction, and then add 32. And that's how we convert between the Celsius and Fahrenheit temperatures. So I take 102 and multiply that by 1.8, and then I add 32 to that, and I come up with something. And I'll leave that up to you to do that in degrees Fahrenheit. It's going to be a large positive number. And then I do this down here for the Fahrenheit temperature. And as I multiply this by 1.8 and then add 32, I come up with a large negative Fahrenheit temperature. I picked up this thermometer here from the software, and I can move around here on the Celsius scale, but notice that the temperatures on the moon are off the scale. This is a normal weather scale, or for the weather here on Earth, and then I can switch from Fahrenheit to Celsius, and that's what I figure I'm going to do here in addition to this problem I just did. So I'm going to scroll down here and make up another couple of problems, perhaps change the color. There we go. So this is besides the problem that I just did. Let's say we have a Celsius temperature. Ooh, geez, maybe I didn't want to do that. That was a little bit too much. Okay, I'll try another color here. Okay, let's say I have a temperature of 74 Fahrenheit. So, nice summer temperature, I guess. That for always smears. Okay, now using this equation up here, I'm going to go the opposite direction. So I subtract 32, which is 42, and they divide by 1.8, and I have to do it on the calculator, and I come up with a rounded 23 degrees Celsius. Let me take a relatively high temperature. So let's say 100 degrees Fahrenheit. And I subtract 32, which is 68, and then divide by 1.8, and that is a rounded 38 degrees Celsius. And then I take, let's say, a relatively low temperature. Well, actually, relatively for us in Alaska, that's not necessarily common if you live in the south of Alaska, but we can hit that temperature definitely. So negative 20, I subtract 32, which is negative 52, and divide by 1.8, and I come up with negative 29 degrees Celsius. Okay, this I actually have to do on the calculator. Of course, I can look at this thermometer here as well. So I go to, my first one here was 100. There we go. And then, okay, 99. I switch over here, 37. As I said, it's a little bit hard to get that exactly onto that temperature. There it's 100. Okay, and there it's converted. 38. And then I had 23 degrees Celsius, which is there, maybe. It's a little bit trickier. So 23 degrees Celsius, I guess 73 or 74 if I go up to 74. It depends on how it rounds or how it converts. I can't get to 74. Okay, so negative 20. And again, it doesn't want to stay there exactly. There we go. Negative 20. And that's negative 29 degrees Celsius. So obviously if I have a thermometer that measures both Celsius and Fahrenheit, then I can just read off one or the other, or I make this long conversion. Now, here's a little thing that could come in handy. These numbers on a temperature scale, they're actually easily converted. These numbers on the temperature scale as far as the weather is concerned are easily converted. If you don't need that much accuracy, for example, you're talking to a tourist and they have no idea what 100 degrees Fahrenheit is, and you say, well, here's an easy conversion. Instead of using this here with the 1.8 and 32, you use instead 30 and a multiplier of 2. So here it is. 100 degrees Fahrenheit minus 30 is 70, divided by 2 is 35 degrees Celsius. 74 minus 30 is 44, divided by 2 is 22 degrees Celsius. Negative 20 minus 30 is negative 50, divided by 2 is negative 25 degrees Celsius. Notice how quick this was. I need a calculator. I can just do it in my head. Because of dividing by 2, it's advantageous to actually have even numbers, so you don't have to think too much. But this kind of approximation you can easily be used out on the street with a tourist, and then you don't have to think much about it. But of course, it's just a side point here for me, or footnote, because the problems that we encounter here, we have to do, I guess, the exact conversion. This is just a very good estimate, as you can see. This is the problem on absolute zero. And it says, a temperature of absolute zero occurs at negative 273.15 degrees Celsius. What is this temperature on the Fahrenheit scale? So, Tc equals negative 273.15 degrees Celsius. And we're using the typical conversion. So, Fahrenheit temperature equals 1.8 temperature in Celsius plus 32, and when you do that, you come up with the absolute temperature in Fahrenheit for absolute zero, and it's going to be a large negative number. And if you wanted to, you could also convert either one of those numbers to the absolute temperature in kelvins. However, that one is being defined as 0 kelvins, or in the Rankine scale, TR, and that is also defined as 0 Rankine. We will be using absolute temperatures. These two are absolute temperatures. Later on, this is not okay. This means 0 kelvins, so absolute temperatures. Later on, when it's important that we avoid negative temperatures, and that's why we need these absolute temperature scales, which are either in kelvins or Rankine. And the Kelvin is associated with the Celsius because there is a simple subtraction or addition of the 273 degrees, and the Rankine is associated with the Fahrenheit because there is a simple subtraction or addition of 460 degrees. By the way, here I'm giving the answer way to this problem. Here you also see the conversion formulas, and as I said, 1.8 times the Celsius temperature plus 32, or if you go the other way around, subtract 32 first and then divide by 1.8. This one here, I would go through Celsius. If you go from kelvins to Fahrenheit, go first through the Celsius and then go to the Fahrenheit. I wouldn't advise doing this one here because you just have to memorize more or pay attention to more stuff. And then here's the simple Rankine compared to the Fahrenheit. These two here are related to that when we change the Celsius to or when we have temperature differences, then the Celsius temperature increase is the same as on the Kelvin scale, and the Rankine is similar to the Rankine, that when we increase with a certain Fahrenheit temperature, then we increase with the same Rankine temperature. That's because the temperature steps are the same for the Rankine and the Fahrenheit as well. They are the same for the Celsius and the Kelvin. That's what they're talking about here, where they talk about temperature intervals. 1 Fahrenheit degree is the same as 1 Rankine degree, or 1 Celsius degree is the same as 1 Kelvin. Another thing I wanted to look at here, now that we looked at, of course we cannot use this thermometer here because our temperature here of absolute zero is off the thermometer. Another thing I wanted to look at is that when we looked at positive temperatures, then the Fahrenheit is always larger than the Celsius, and now we've been looking at the lowest temperatures so far in the negative, and the Fahrenheit temperature is lower than the Celsius temperature, and that means they need to meet somewhere. And one way of looking at that, figuring that out, would be to do the algebra, writing this down here. So TF equals 1.8 times TC plus 32, and now is saying that, well, in order to figure out where they meet, so TF meets TC, that would be to say that the two are the same as far as the value is concerned. So I can just write down here TC, or I should write down here TC, do the algebra on this, and when I do the algebra, you may do that yourself, you come up with that temperature is negative 40 degrees Celsius. And indeed, when you take negative 40 degrees Celsius and you multiply with 1.8, you come up with negative 72. And when you add 32 to negative 72, you come up with negative 40 Fahrenheit. So, as I said earlier, in the positive, the Fahrenheit temperatures are larger than the Celsius temperatures, and in the far negative, the Fahrenheit temperatures are smaller than the Celsius temperatures, and that means they have to meet somewhere, and well, this is where they meet. -40 Celsius, the same as -40 Fahrenheit. This was just, again, a footnote to this particular problem. This is the problem about shrink fitting, and it says a commonly used method of fastening one part to another part is called shrink fitting. A steel rod has a diameter of 2.0026 centimeters, and a flat plate contains a hole whose diameter is 2.0000 centimeters. And this is the best image I could find. So here's this round piece here that fits into this hole, respectively, is actually too large, and then you cool it and it will contract, and then you can fit it in there, and when it returns to normal temperature, then it will be stuck to that flat plate. As I said, that's kind of the substitute image that I came up with. So the problem continues. The rod is cooled so that it just fits into the hole. When the rod warms up, the enormous thermal stress exerted by the plate holds the rod securely to the plate. By how many Celsius degrees should the rod be cooled? Okay, let's see what we have given respectively, what is being asked for. They're asking by how much it has to be cooled, so they're asking for a temperature difference. They don't tell us what the original temperature is, but we will see from the equation that that is not necessary to know, but instead we need to know what the temperature difference is respectively. That's what they want us to figure out. Okay, let's see. What is given is the original diameter, D0, hold on. Might as well write this again here. So D0. What is given is the change in the diameter, delta D. There we go. What else is given is the material, the steel here, and now we have to look at an equation before I write this one here down, and that's the equation on thermal linear expansion, which is delta L equals alpha times L naught times delta T. And of course, our delta L and the L naught here, the length, are the diameters and the change in diameter that we have here. By the way, somebody could argue that, well, it happens in 2 dimensions, but still it's a diameter in one dimension and the diameter in the other dimension that needs to change. So the equation is applicable either way, and we only apply it to one diameter, and it would apply to the other one simultaneously. Anyway, what we also know is the alpha, the coefficient of linear thermal expansion for steel, and then what we need to figure out, in this case they're asking what the delta T is, so we're going to do the algebra. Delta T equals delta L, which is the 2.0026 centimeters, I believe it said in the problem. Yes. Okay, I actually didn't make a mistake a moment ago here. Of course, that is the 0.0026 centimeters, that delta L or delta D, because that's by how much it has to shrink in order to fit into the hole. And then divide that by the alpha, which we look up in the book, and it's given as, for steel, where did it go? I'm trying to find, oh, there, iron or steel, 12 times 10 to the negative 6, and the unit on that is per Celsius degrees. And then we also have to divide by the original length, which would be 2.0026 centimeters. Notice that we don't have to convert to meters on this one, because this one is in centimeters, this one is in centimeters, so the two divide out, and the only unit that survives is the reciprocal of Celsius, which is the unit for the alpha, and because it's a reciprocal and this thing is in the denominator, it goes back to the numerator, and we have a typical Celsius degrees here as the unit. This one here is going to come out to a positive number, even though they're saying it's cooling. I mean, if you wanted to have a negative number, I guess you could call this one here. It has to shrink by 0.0026 centimeters, so you put a negative in front of it because it's shrinking, and then you would also come up with a negative temperature. But either way, you know, you're going to come up with 100 some degrees. Top of my head is what it is, and you can deal with that as either saying that's a positive number or it's a negative number. Either way. This is the problem on these two thin strips that kind of look like a bimetallic strip, a little bit different. As the drawing shows, two thin strips of metal are bolted together at one end and have the same temperature. One is steel and the other is aluminum. The steel strip is 0.10% longer than the aluminum strip. By how much should the temperature of the strips be increased so that the strips have the same length? By the way, I said it's kind of looks like a bimetallic strip, but it isn't. Bimetallic strip is soldered or glued together all the length through that, so that when one of them expands more than the other, they actually have to curl, and that's what you have, for example, in your temperature control, your some mechanical thermostats. That's the way they work on that bimetallic strip. In this case here, they're only bolted together here at the end. That means they can expand independently, and the idea is that this looks exaggerated here. Well, maybe this kind of looks like almost 10% around there, but that the aluminum is expanding more over a given temperature interval than the steel is as it is expanding, and then when the two are done, they're going to reach the same point at the end. So if I do this one here, that the steel expands, for example, to here, there, and then the aluminum as well expands to here, and then the two lengths are equal. And in this case, because they're not glued or soldered together here, they're not curling, they're just expanding lengthwise. Okay, anyway, let's see what we have given. First of all, delta T is what they're asking about. Oops. Delta T, question mark. What, let's see, alpha is given, of course, for both of them. We just looked it up in the book for steel and aluminum. And then we look at delta L and L, 0, and neither one of them is given. They don't say by how much they expand. They don't say what the original length is. They say by how much percentage-wise they expand. And that then means that actually the delta L over L0 says, and actually I take that sentence back. I'm not going to finish that sentence because not even that is given, not even the ratio between the two. What is given is that the, let's see, steel strip, that the L0 divided of the steel, ST, divided by the L0 of the aluminum, that is given, and it is 0.1% longer. So I'm going to put that 1 right there. And then we can see that this one here is 0.10% longer, and of course this is a ratio here, so it doesn't have units. So that's basically what's given. I wish they would give us actually the original lengths. Apparently we don't need them because the outcome is going to be the same. So for example, if the two strips are each 10 centimeters long, I mean one of them 10 centimeters and the other one 11 centimeters long, or if one of them is 1 meter and the other one 1.1 meter long, the outcome, which is the temperature difference here, would be the same either way, because the aluminum would expand in the same ratio no matter what the original length is. But as I said, I would just prefer to have the original lengths given, because other than that, it's actually going to be kind of some, well, to say the least, interesting algebra. So let me get started on this one here. As I said earlier, the steel is going to expand to a certain length, and the aluminum is going to expand to a certain length. So when everything is done, the length expanded by the steel equals the length, the total length expanded by the aluminum. Okay, and then the expanded length of the steel would be the original length of the steel plus the increase in length of the steel, and the expanded length of the aluminum would be the original length of the aluminum plus the delta L of the aluminum. Now that much we know, this one here, and then just plugging in this one we know. Is that going to lead us to a solution? Well, I actually had to look at the solution manual to figure out that, oh yeah, that's the way to do it. So I kind of have a head start here that this one indeed will work out, and that even though this is kind of interesting, I wrote down an equation here and I don't know this, I don't know that, I do not know this, I do not know this. I have like 4 unknowns in here. I basically just know that this one is equal to that one, and that this one here is 0.1% longer than that one. So actually I have kind of like 3 variables here. Okay, well, let's see what happens next. I'm going to write this one here down again, L0 steel. And now the delta L for the steel I'm going to write as alpha steel. And finally, that one I do know, times the original length of the steel times the delta T, and that equals the original length of the aluminum plus the alpha of the aluminum times the original length of the aluminum times delta T. Okay, let's see where that leads us. On the left hand side, I noticed that I have the same here, L of the steel, L of the steel, so I'm going to factor them out. So L O steel times parentheses 1, as I factor it out, of course a 1 stays behind, times the alpha steel delta T, there we go, and then equals, and here I do the same thing. I'm able to factor out the aluminum, original length of the aluminum, and therefore what stays behind is 1 plus the alpha of the aluminum times delta T. Okay, and now I notice something here. Here's the length of the steel, and here's the length of the aluminum, both factored out. So if I get one to the other side, I can readily introduce that factor here, 1.0010, by how much the by which amount the steel is longer than the aluminum. And then I truly, after I did this, I truly just have one variable. So as I said, I struggled with this problem when I taught it in class, in a regular classroom setting, and because it's not intuitive. You know, sure, we know this one here, we know this one, but then with the second step here, introducing kind of like 3 or 4 variables, you know, is that going to lead to a solution? And indeed it does, but it's not totally intuitive. In any case, I'm going to do the algebra here a little bit more. So I divide this one here, divide by the original length of the aluminum, and therefore I'm going to have 1.0010 introduced instead of the fraction of the original length. And then here's the same thing, and I don't think it would be nice if I could just copy that, then I don't have to write it all down again. Let me try that. Yeah, there we go. Whoops. Alright, I think that just took as much time as just doing it. Okay, so I divide by that length of the aluminum, and therefore on the left hand side I have that factor 1.0010. I wonder why my handwriting has never improved, and I apologize for that too, that it hasn't. Okay, in the next step, I'm going to multiply this in here, so I'm going to have 1.001 plus 1.001 times the alpha and the delta t, and the right hand side stays the same, but then I noticed that I subtract the 1 from the left hand side, and so that will be a 0.0010. So this here multiplied minus that 1, and then on the right hand side I subtract this here, multiplied of course with this one here, from this one here, so I'm going to have alpha aluminum minus 1.0010 alpha steel. So notice this one here minus this here, multiplied with that 1.001, and then factored out the delta t. That's why I didn't write the delta t down yet. Delta t. And now I can just plug in numbers and come up with what the temperature increase should be. So for that one I have to look up the coefficients of thermal expansion. So I'm going to have 0.0010 divided by parentheses. The alpha for the aluminum is 23 times 10 to the negative 6, and then I subtract from that 1.0010 times the aluminum for the steel, which comes out to 12 10 to the negative 6, and I come up with 91.008, and looks like we have two significant figures. So 91 Celsius degrees is the result. This is the problem about the gas tank. And it says, suppose that the steel gas tank in your car is completely filled with, then the temperature is 17 degrees Celsius. How many gallons will spill out of the 20-gallon tank when the temperature rises to 35 degrees Celsius? The reason I took this really old car is because I figured that, well, here we could, maybe this is the gas tank. I actually don't know that, but at least it's on the outside, so let's assume it is, and we could actually see it. And then, of course, if it's still open, then the gas can spill out, and if it's not open, then with a rise in temperature, there could be some pressure exerted from the inside, and I don't know how big the stress and the strain is, but I'm sure it's not that great for the gas tank, and we kind of know that on a hot day we should not fill in the gas to the brim if we don't drive the car right away, because it will expand and could induce some stress, and that could be pretty bad to the gas tank and the car and the drivers, passengers. Okay, let's get started on this one here. So let's see what they're giving and what they're asking for. They tell us what the increase in temperature is. It's 18 degrees Celsius, or 18 Celsius degrees. So it starts at 17 degrees Celsius, which is in the neighborhood of like 64 Fahrenheit, and then the temperature rises to about 100 Fahrenheit. 35 degrees Celsius times 2 plus 30 is 100. So over that temperature range from 64 to 100, which is 36 or Fahrenheit, or 18 Celsius. I mean, kind of round it on the Fahrenheit part. Then they tell us that it has a volume of 20 gallons, so they tell us that the original volume is 20 gallons, and they tell us that this is a steel gas tank, so oops, not an alpha, but the beta, because that applies for volumetric expansion. And then we're supposed to come up with the delta V, because it says by how much does it flow out. So delta V, and then I just noticed that, you know what, the gas tank will expand, so beta delta T at beta steel, but of course the gas will expand as well, and that's of course what it's about. So I should make a double check mark here. We have both given the volumetric expansion coefficient for both the steel as well as the gas. Now, when I look in the table on the coefficient of thermal expansion for volumes, I can see that that one for gasoline is quite a bit higher than that one for steel. So 950 10 to the negative 6 compared to 36 times 10 to the negative 6. That's almost 30 times higher. So that means actually that the expansion of the gas tank itself is rather negligible compared to the liquid, the gasoline itself, and we'll see that later when we subtract one from the other, that it won't have mattered as much. Okay, so here is for the gasoline, and it says delta V equals the beta for gas times the original volume of the gas, and I should make actually double check mark here as well for the volume, because the volume both for the gas as well as for the gas tank are given, and both of them are 20 gallons, and then times the delta T, which of course is given as 18 Celsius degrees. Now here one could think that we should convert to something more metric, but we actually don't have to. This one here is per Celsius degrees. This one here is Celsius degrees, so that units from these two divide each other, and then what we have left here is gallons, which means that the increase in volume is also expressed in gallons. So we can just leave it that way and come up with a result in gallons. And so I'm gonna try to push this a little bit over here. Oh, I can't. Never mind. Oh, I can push the car a little bit other way. There we go. And so equals, and then what I come up with is that 950 10 to the negative 6 times the original volume was 20 gallons times the increase in temperature is 18 Celsius degrees. So 0.342 gallons, that's by how much the gas expands. That's definitely not negligible. That's a third of a gallon. 3.42 as the temperature rises from the mid-60s on the Fahrenheit scale to 100. I'm going to write this as 3 significant figures. The problem actually suggests only 2, but you'll see here that in a moment when I do this here now for the gas tank itself, that I do need that extra figure. So the gas tank itself is going to be the same kind of equation. That's why I tried to copy that actually. Whoops, there is no delta. There we go, and then plug in the numbers, and that was 36 10 to the negative 6 times volume is 20 gallons again, and times 18 Celsius degrees, and I'm going to come up with 0.013 rounded, and then I subtract the 2. So minus, because now that the gas tank is this much larger, it can accommodate that much more gasoline, and so actually a little bit less than the number calculated here will spill out. So as I subtract the 2, I'm going to come up with 0.329, which is going to be a rounded 0.33, obeying the 2 significant figures. So 0.33 gallons is the correct answer, so pretty much exactly 1/3 of a gallon. Quite a bit. There's one of the problems about blood, and it says blood can carry excess energy from the interior to the surface of the body, where the energy is dispersed in a number of ways. While a body is exercising, 0.6 kilograms of blood flows to the surface of the body and releases 2000 joules of energy. The blood arriving at the surface has a temperature of the body interior 37.0 degrees Celsius. Assuming that blood has the same specific heat capacity as water, determine the temperature of the blood that leaves the surface and returns to the interior. One of the things to notice is the significant figures. Look at the 0.6 kilograms and then the 2000 joules, both only one significant figure. So at some point that's what we have to deal with, and then later on when we calculate the temperature difference to only one significant figure, that's then what we have to subtract from the 37.0 degrees Celsius. So to begin with, I realized that they want from us the absolute temperature, but here with the specific heat capacity, we're calculating a delta T first, so that's the question mark here, and then later on we're going to subtract that from the 37.0 degrees Celsius. Okay, let's see what else is given. The mass of the blood is given. Then the amount of energy is given. And then the original temperature is given, but I said we use that later. And then it says that the specific heat capacity of blood is the same as that of water, or approximately so. So I found one that lists at 3.78, and that compares with water, which is 4.136, I believe, or 4,186, depending on what kind of units we're in. So 4,186 compared to 3,780, and so which means pretty high, just as for water, which is by far the highest of most common materials. So they say, use the one that we have for water. So that one is given as 4,186, and so I'm going to write down lowercase c, and then it's straightforward here. These variables here already suggest that I have to use the equation for specific heat. So Q equals C times M times delta T, and we're supposed to figure out delta T, and that n equals 2000 joules divided by 4,186 joules per kilogram in Celsius degrees. Yes, that's correct. And also divide by the 0.6 kilograms, and you come up with a temperature decrease in Celsius. And technically what we should do is, as the energy is being released, it's losing that amount of energy, so we should treat this one here as a negative 2000. So Q is given as 2000, negative Q 2000, so we come up with a negative temperature difference, and then we add to that the original one, the 37.0 Celsius degrees, and as we do that, we come up then with plus something, and that's going to be in Celsius degrees as well. And I can just tell you it's a little bit, let's see, it's a little bit less than 1 degree Celsius. And when you write this one in one significant figure, because that's what these numbers here suggest with the 2000 and the 0.6 kilograms, one significant figure, so it's going to be point something. As you subtract that, you're going to come up with 36 point something, and because you're subtracting that one significant figure here, as you're subtracting this in the front here stays. It had originally nothing to do with the calculation over here, and then as I said, you're going to come up with something right here. At this point, I may want to say something about the delta T, the difference in temperature, and being expressed in Celsius degrees versus kelvins. Notice also that the C is expressed in joules per kilograms and Celsius degrees, but it could also be expressed instead by divided by kelvins. And we had the same thing for the linear thermal expansion. It was the units were in 1 over Celsius degrees, but it could be also in 1 over kelvins. And the reason is that for temperature differences, which is Celsius degrees or kelvins, that we can use either one, because if you're writing 37 degrees Celsius going down to, let's say it is 36 degrees Celsius, that's a difference in 1 degree, but notice if you wrote this in kelvins, you would have 310 kelvins going down to 309 kelvins, and the reduction is just the same, 1 Kelvin. And that's why for temperature differences, Celsius degrees and kelvins are interchangeable. And I also put that in Blackboard kind of as a disclaimer onto where you're linking to these videos, saying that for temperature differences, it doesn't matter if you're in kelvins or Celsius degrees as long as you're consistent. For absolute temperatures, which we will encounter in the next few chapters, that is important that we have to be in kelvins. But here for temperature differences, either way, Celsius degrees or kelvins is fine. This is the problem about the thermometer, and it says, ideally, when a thermometer is used to measure a temperature of an object, the temperature of the object itself should not change. However, if a significant amount of heat flows from the object to the thermometer, the temperature will change. Here we're going to calculate something where, the thermometer itself, as we're putting it into water, does influence actually the temperature, so it's going to change the temperature of the water. Notice that in the lab on specific heat capacity, where I'm asking you to write down as many errors as possible in your conclusion, that would be 1. We didn't determine the mass of the thermometer or figuring out what original temperature it was, and kind of neglected its effect on that it has mass and therefore specific heat, its effect on the experiment itself. So as I said, for that one, write it down as an error. Here they actually let us calculate what the effect is. Anyway, I haven't finished the problem, so it continues on. A thermometer has a mass of 31.0 grams, a specific heat capacity of 815 joules per kilogram in Celsius degrees, and a temperature of 12.0 degrees Celsius. It is immersed in 119 grams of water, and the final temperature of the water and thermometer is 41.5 degrees Celsius. What was the temperature of the water before the insertion of the thermometer? Okay, let's see what's given. The mass of both the thermometer and the water are given. The specific heat capacities of both the thermometer as well as of water are given. I mean, it says in here, it's water, so you look it up. And the one for the thermometer is given as 815 joules per kilogram in Celsius degrees. And when you look in the table, it's pretty close to what glass is, so that makes sense. Using a glass thermometer with some mercury in it. And then we are supposed to figure out what the temperature is, but in all likelihood we should figure out what the temperature decrease is for the water. And then take that one and add it to the final temperature of the water to get the original temperature of the water. So this one here we're trying to figure out. So let's see where we start. For the thermometer itself, we would have that Q equals the specific heat capacity times the mass times the delta T for the thermometer. And now we have to see, well, this delta T, what we're supposed to figure out here is for the water. What about the thermometer? Well, that's actually given in the problem. So where it says that the thermometer starts at 12 and then it warms up to 41.5 degrees Celsius. So that means that the difference of 29.5 Celsius degrees is the temperature difference for the water, so that one is given. So one of them is given and the other one is what they're asking for, and we can kind of see that we have 6 variables, 5 of them are known and only one unknown. Okay, so this one here is the thermometer. Then for the water, it's the same kind of equation, equals C times M times delta T. Okay, that was supposed to be looking a little nicer. So there's the C for the water. And then we realize that the water being at a higher temperature than the thermometer is, the amount of heat that flows out of the water and the amount of heat that flows into the thermometer are equal. That, of course, has to do with the conservation of energy. So whatever heat flows out, which we don't have to calculate that, but simply what we have to say is that the two heat flows are the same, so the heat flow into the thermometer is the same as the heat flow out of the thermometer, out of the water. And yeah, technically this one here should be negative and this one here should be positive. And I think I can write this by saying that, yeah, this one here, the heat flow is negative, so therefore I put another negative in front of it to make this one here positive for the thermometer. We can actually say it that way because this temperature increase, this delta T is a temperature increase, so the whole thing is going to be positive. This delta T is a temperature decrease, so the entire heat is negative. So I'm going to write it like this here, and then I'm going to plug everything else in, so it's C times M times delta T for the thermometer, and that equals then negative C times M times delta T for the water. Could have also written H2O there. So delta T for the water therefore comes out to C M delta T for the thermometer. This one here all being given 815, 31 grams, and that was 29.5 degrees Celsius. And here we have C, the 4,186, and this one here is 119 grams, and there's actually a negative in front of this. And then, oh, by the way, this one here being in grams and this one here being in grams, that's why we don't have to convert it to kilograms, because the grams readily divide out. I'm going to make this negative hopefully look a little nicer. Okay, so that way here, yeah, this one here being 4,186, this one being 119, you come up with something, and this one here is then going to be the temperature decrease of the water in Celsius degrees. It's going to be in a neighborhood of a little bit less than 2 Celsius degrees, and that's by how much the temperature decreased. And then of course we would have to add that number here, or subtract the negative number, to the to the final 41.5 degrees Celsius, and therefore, yeah, so subtract this one here, and this looks kind of weird. So therefore we're going to come up with something like 43 point something. Again, my 4 always looks miserable. So 43 point something, you'll see that that's what you come up with, the original temperature of the water. Again, that temperature difference, this one here being the original, this one here being the final temperature, means that there was a temperature decrease, and that's why this one is a negative. And again, that negative arises from here and originally here, because this one is a negative heat flow to begin with out of the water. This one is into the water, into the thermometer, so this positive, this one being negative. It needs that negative in order to make these two sides equal. This is the problem on the metal forging, and it says, at a fabrication plant, a hot metal forging has a mass of 75 kilograms and a specific heat capacity of 430 joules per kilogram in Celsius degree. And when you look in the table, that could be steel. Its specific heat capacity is pretty close to that. To harden it, the forging is immersed in 710 kilograms of oil that has a temperature of 32 degrees Celsius and a specific heat capacity of 2,700 joules per kilogram in Celsius degrees. The final temperature of the oil and forging at thermal equilibrium is 47 degrees Celsius. Assuming that heat flows only between the forging and the oil, determine the initial temperature of the forging. So the clip art that I found here is this one here, some kind of oil drum here, so we assume that originally is at 32 degrees Celsius, which is in a neighborhood of 95 Fahrenheit. and then we put some metal in here, and that's kind of the only thing I could find here in the clip art on the software. And then this one here is really hot to begin with, so I should maybe shade a little bit reddish, it kind of starts to glow reddish. And we put it in there, and it sizzles a whole lot here. Some of the oil, I guess, well, may evaporate upon contact, but they actually exclude that, so they exclude the latent heat of evaporation in this problem here, and just say, hey, the oil heats up uniformly to 47 degrees Celsius, and this one here then cools down to 47 degrees Celsius, and we're supposed to figure out what's the original temperature, respectively. We figure out first what is the temperature decrease of the metal here, and we do have given the temperature increase of the oil. We have given the mass of both the metal and the oil. We have given the specific heat capacity of both the metal and the oil. And when you look at that, it shows that the algebra is going to be the same as in the previous problem. So all I have to do is paste that algebra in here, and instead of wasting your time this time around, I already wrote it down as that. For the metal, the heat flow is this. For the oil, the heat flow is that. Then the heat flows into the oil, so this one is positive. The heat flows out of the metal, so this one is negative, and therefore in order to equate to here, I put an additional negative in here. So this is a negative of a negative, making that positive then. And then this one here is for the oil, this one here is for the metal, this one here is for the oil, this one here is for the metal. So you come up with some kind of temperature difference. This one here will come out to be a negative number, a relatively large negative number in Celsius degrees. And then the final temperature was 47 degrees Celsius. Always that 4. Never get rid of that. 47 degrees Celsius was the final one. So you add just this number here to it, and you come up with that the original temperature of the metal forging, so T0 of the metal forging, was a pretty large number in Celsius degrees, in the neighborhood of 900 or so. So this one here comes in, therefore, also up to kind of like a decrease of almost 900 degrees Celsius down to 47. That means the original temperature was somewhere around 900 to 1000 degrees Celsius, and you'll figure that out. Again, everything is given here. This one is given in the problem as, what was that, 430 joules per kilograms Celsius degrees. The mass here is 75 kilograms. The delta T here for the, oh, I'm sorry, hold on. This is for the oil here. So this, what I just said, 430 and 75 is down here, and then up here is for the oil 2700 and 710 kilograms, and then the delta T for the oil is 15 Celsius degrees. Everything is given. You come up with the numbers. This is the problem on the passive solar house, and it says, in the passive solar house, the sun heats water stored in barrels to a temperature of 38 degrees Celsius. The stored energy is then used to heat the house on cloudy days. Suppose that 240 million joules of heat is needed to maintain the inside of the house at 21 degrees Celsius. How many barrels? One barrel equals 0.16 cubic meters of water are needed. So here I took a couple of images of the internet, and let's see what shows here. This is kind of original passive solar house. There's no water in here, and the winter sun, as it says here, would heat the inside of that room, and then actually you would have pretty good heavy rock here, massive rock that would then absorb that heat from the winter sun and then could give it to the rest of the house, respectively, radiated out here and radiated back into this particular room. In the summer, with the sun standing higher, it's not directly shining in, but I've been in a house like that, and it's pretty hot in the summer, this particular room, and in the winter it has a really nice temperature. Anyway, that's what it is. And then way they describe it here is this particular one here with the water. That's one way of doing it. So the heat reaches this one here, and then there's an antifreeze fluid in here. So as I said, this is one other technique. Neither one of them is exactly the same they're talking about here in the problem. So there's an antifreeze in here, and then there's a pump, and it goes into the water tank here, which then heats the water. Either way is kind of considered passive solar heating, as contrasted to the active solar house, which would be photovoltaics, but there's not it. So we're heating water here. So let's see what's given in the problem. They tell us what the heat flow is. So Q is given. They tell us what the temperature difference is. It's 17 Celsius degrees, and what it means is that the water does heat up to 38 degrees Celsius, but then gives off its heat to the rest of the house, maintaining it at 21 degrees Celsius, including the water itself. So that's why the temperature of the water itself goes down to 21 degrees Celsius. And of course, it says it's maintaining, it's actually not increasing its temperature, because the house is losing heat to the outside anyway. So we're kind of looking at a winter house here. Of course, if the outside temperature is 35 degrees Celsius, we don't want to have any heating going on anyway, and we'd be rather using the air conditioner than trying to heat the house. But so this one must be like in the fall or spring or winter, where the outside temperature is lower, so we're losing heat to the outside, and therefore we need to heat it, and that's done with this solar passive heating. Okay, so delta T is given. The mass of the water is not given. However, they want to know the volume, and the volume, of course, is linked to the mass by the density of the water. So that's why we come up with here a question mark for the mass, and once we figure out what the mass is, we can figure out what the volume is of the water. They ask us to figure it out in barrels, but we calculate it first into cubic meters, and then we convert it to barrels. And then, of course, the specific heat capacity of the water is given, and considering these variables here, the algebra is going to be straightforward. Respectively, there really isn't any algebra. We just write down the equation for specific heat. So Q equals C times M times delta T, and then we're supposed to figure out what M is. So mass equals energy divided by C and delta T. And then, yeah, we don't have to figure out what the mass is, or figure it out first, but we have to figure out what the volume is. So mass equals density times volume. So actually here, volume, therefore, when I substitute that, density times volume for the mass, and then divide by the density, I'm going to come up with this one here, Q divided by density, specific heat capacity, and delta T. This one here being the incredible 240 million joules, the density 1,000 kilograms per cubic meter, the specific heat capacity 4,186. Notice that this is a huge number, but these two are relatively large as well, in the thousands each of them. And then the delta T, that would be the 17 Celsius degrees that the water then cools down from. After being heated to 38, it cools down to the ambient temperature in the house of 21 degrees Celsius, and we come up with a certain volume in cubic meters, and then you use the conversion in the problem that tells you then how many barrels of water are needed. This problem is about sweat, and it's kind of the only clip art I could find with this crocodile running and sweating, and I tried to look that up, and it didn't say anywhere, couldn't figure it out anywhere if crocodiles are really sweating. I kind of really doubt that reptiles would be sweating, but as I said, that was the clipper that I found that actually showed some sweat. Oh well. So the problem says the latent heat of vaporization of water at body temperature of 37.0 degrees Celsius is 2,420,000 joules per kilogram. To cool the body of a 75 kilogram jogger, average specific heat capacity is 3,500 joules per kilogram in Celsius degrees, which is a little bit less than our water. As we know, we're mostly made of water. And that to cool the body by 1.5 Celsius degrees, how many kilograms of water in the form of sweat have to be evaporated? So let's see what they tell us. They tell us the temperatures, respectively, the delta T of 1.7 Celsius degrees, and that one is done in order to, due to the exercise, the body of course heats up, and then it has to be cooled back down to 37 Celsius degrees. The problem doesn't say that, but we can kind of figure that out from, well, having some extra knowledge of our own. What else is given is the mass of the jogger on one hand. On the other hand, we're supposed to figure out what the mass is of the sweat, which would be basically water being sweated out. And what is given is the specific heat capacity of both the jogger as well as the specific heat capacity of the jogger is given, and then the latent heat of vaporization of water is given. So I'm going to write LV down here. So kind of a different problem here. In previous problems we looked at that we had specific heat capacity given, and one of them would be cooling down and the other one would be heating up. Here what's happening is that the body is supposed to cool down, and then that heat that it's losing is being used to actually vaporize the water that's under the skin or on the skin, and that then becomes water, steam, vapor, and that of course is the sweat that we're losing, and as we know, that's a cooling process. Okay, for the body itself, we have that the amount of heat flow equals its specific heat capacity times the mass times the temperature difference. With all of these given, so we could actually calculate how much heat the body is losing. By the way, that also means that because this one is a negative delta T here, that this one here comes out to be negative. And then for the water, that means the sweat itself, the heat that absorbs, and that's what would be then positive, is mass times the latent heat of vaporization. Notice that of course there is no delta T associated with it because it's a phase change, and a phase change, what's important is that it goes from one phase to the other one, and the latent heat is important, and there is no temperature change. Okay, anyway, this one here is being negative, this one here is being positive, so when I equate the two I would write Q of the water equals negative of that already negative number of the body, and then I plug in things, so I'm going to have M times LV of the water, and that equals negative all the rest here of the body. And then we're supposed to figure out what the mass is of the water. And therefore that's going to come out to everything that's on the right hand side, which I mentioned just a moment again, and divide that by the latent heat of vaporization for water. So MW equals underline, and again this one here is given as, let's see, that was 3,500 joules per kilogram Celsius degrees. This one here is 75 kilograms. This one here is actually negative 1.5 Celsius degrees. And then with this negative here and that introduced negative that I introduced over here, that of course then becomes a positive numerator. And then divide that by the 2,420,000 joules per kilogram, the latent heat, and so that one here comes also out to a positive number for the mass. And when you look at the units, you come up with a nice kilograms for that one. And that's how much mass would be evaporated. It's going to be in the neighborhood of almost half a pound. And I looked that up, and for people who are exercising a lot, yeah, there are losing quite some mass due to sweating, and if they're really going on a triathlon, you know, that's in the neighborhood of several pounds, and that's also why they have to keep in taking mass in. Besides that, they do that per water electrolytes, that they also rehydrate themselves. This problem is about the bullet, and it says it is claimed that if a lead bullet goes fast enough, it can melt completely when it comes to a halt suddenly, and all its kinetic energy is converted into heat via friction. Find the minimum speed of a lead bullet. Initial temperature is 30 degrees Celsius for such an event to happen. I tried to look that up, and I couldn't find a single website that be talking about that the lead bullet actually on impact could melt. So that's why I guess the problem says it is claimed. So anyway, let's see what we have given. And that would be the original temperature of the lead. So T0 is given as 30 degrees Celsius, and that's practically it. What they want to know is the speed, so I'm going to write down V here. I'm going to write this towards the right just in case I need more space here, because here we should write down thermodynamic variables including the mass and so on. Notice that actually the mass isn't given. And then we're supposed to figure out what the velocity is, which when we looked in this chapter there isn't a single equation that includes velocity, so let's see how we could figure that out. On the mass, that the mass isn't given, we could have a hunch of that mass must divide somehow out of it. So if we take a bullet that is twice as massive as another lead bullet, then the speed of the two is still going to be the same, and the needed speed is still going to be the same for both of them, and they would melt at the same temperature. But in any case, that's actually what they want to figure out. Oh, I'm sorry, the velocity here is what they want to figure out. But we could say that, well, we probably do know what the melting temperature of lead is. So I'm going to give that as a given. And indeed the book says that for lead that melting point is 327.3 degrees Celsius. So the lead needs to heat up almost 300 degrees in order to get there. That means also that we definitely need the specific heat capacity for lead, which is given in another table. Top of my head, it's 128 joules per kilograms in Celsius degrees. And then it's supposed to melt, which means I'm going to give it a little bit more space here. Let's see if I can do that. Nope, can't do that. So I'm going to take the V off here and write it even further to the side. V is what they want to figure out. Because then it has to melt. That means that we have to write down LF, which is given in the book, latent heat of fusion going from a solid to a liquid. My F just never looked nice here, so that's given. And as I said, the mass here, well, it's not given, but I think we can have a hunch that somehow divides out. Okay, the lead starts at 30 degrees Celsius, and I couldn't find a good picture of such a bullet, so that's why you don't see one here, and maybe I should just draw one. Do I have some gray here for lead? Oh, there's some gray. There we go. And then I could, I guess, draw this bullet here. There we go. good enough. Okay, and that bullet, whoa, no, I don't have my nice blue anymore. There we go. Now that bullet starts at 30 degrees, and by the way, it has a certain speed. It starts at 30 degrees Celsius, heats itself up to the melting temperature. That means in order to get there, it has to be a certain amount of heat going in, which is the specific heat. So C times M times delta T. This here is the almost 300. It's like 297.3 Celsius degrees. And then it has to melt, which means there has to be more heat going in order to melt it. And I could call it QF, the one for the latent heat of fusion. So I have to add that to that. So mass times the LF that is given in the table as being, I think it's 23,200 joules per kilogram in order to melt lead, and that energy has to come from somewhere in order to melt the lead. Well, what does it have to do with velocity? And really the only conclusion we could come up with is that it's the kinetic energy, and of course when it comes to a stop, that kinetic energy has to go somewhere. And if you look back in the chapter on energy, then you find out that when a kinetic energy is gone in an inelastic collision, so it actually kind of puts us into energy and momentum chapters, that then goes into heat. So therefore the original kinetic energy becomes the heat in order to heat it up to the melting temperature, and then actually at the melting temperature in order to melt it. And so that kinetic energy is, of course, 1/2 mass times velocity squared. And as I said earlier, a hunch that mass divides out is justified. It appears in every term, so we can take it out. And then the velocity, well, just a couple of algebra steps here. Multiply by 2 and take the square root. So we're going to have 2 times C times M delta T plus M LF, and take the square root. And when you take the square root, you're going to come up with positive and negative result. Let's shoot it to the right, and so we come up with a positive result, and everything is given in standard units, and so therefore for the velocity we have to come up with meters per second. Oh, then I did make that mistake. Whoops. I already divided the mass out, and then I wrote it down again. I should have just done this here. Could have avoided that mistake. So, a case. Oh yeah, and then I made a second mistake. That 1/2, you're getting rid of it. Of course, everything on the right hand side is multiplied with the 2. So we have 2 times the 128 times the 297.3 plus 2 times the, what was that, 23,200, and then take the square root of that, and the result of that is going to be in the neighborhood of like 1,000 feet per second. Of course, you're going to come up with meters per second, and you can see that, well, that kind of makes sense. That's kind of how fast bullets are, 1,000 feet per second or even faster. And so that's why it says there is the claim, so theoretically it's possible. If it actually happens, well, that's a different thing. You know, there's damage to the target, there's damage to the bullet, there's heat dissipating into the air as well as the target. So the bullet may or may not melt after all, and that's why they say in the problem that's a claim, and that's why possibly I couldn't find anything. In any case, you do come up with a velocity in meters per second.